Welcome to a lecture on crystal symmetry. I know that later today or one of the coming days you're going to learn more about diffraction from crystals. So in that sense, knowing something about how crystals can be described in terms of symmetry may be a good idea. And you probably already know something about crystals. So I could ask you, what is a crystal? Any rough idea about what a crystal is? Yes,
it's something with lens.
Something with a lens, exactly. So basically, that's some sort of periodicity, right? You have some kind of translational symmetry. And one of the most easy ways to start or embark on looking at crystals is to look at hard spheres and how they pack. And you probably have seen something like this before, closed packing of spheres. And you can do that in several ways. You can make a square array of circles, but if you really want to make a closed pack, then you have to change the lattice a little, and they will have the minimum distance between the spheres in this way, right? In 2 dimensions. But if we go to 3 dimensions, things become a little more complicated, right? So if you go to 3 dimensions, and this is the 2 dimensions, you can see there's a kind of a hexagonal pattern appearing. And if you go to one more dimension, you can then envision putting on spheres in different ways on top here, but they will fit into these holes here, right? And so you have 2 layers here now. And that's still something that can only be done basically in one way. But once you put a 3rd layer on top, then it can be in 2 different positions. Either it can go into one set of holes or another set of holes, basically, between or fitting into layer 2. And you can see that probably in this way here, you can have the 3rd layer, you will have to choose between either putting the blue spheres here or the red sphere here, right? And then you get 2 different types of closed pack structures. You get the cubic closed pack structures or the hexagonal closed pack structures. You're physicists, right? You like this type of systems, right? Whenever you choose a system, you choose something like this. But I'm a chemist, I'm not so fortunate. And things become more complicated when you have larger systems and more atoms, even molecules. Of course, you can also make really difficult systems just looking at ionic compounds. But now I have one more slide with just showing you from the side how these closed packed structures look like. But if we want to describe more complicated systems than just this type of system, then we have to think of ways of doing that. So you can see here something a little more complicated, right? It's hard to see just from this slide how we should describe the symmetry in this system. And I'll just show you a few more of these examples. So now I'm using a program that can visualize structures in 3D. So here's the same structure as we had before. Now I can rotate it, right? And I can choose a lot of different structures here. And you can see these are structures from what's called the Cambridge Structural Database. So these are basically all structures determined by diffraction techniques within the last 50 years. There's about 700,000 structures determined. And we are not going to go through all of them, but you can see they come in different flavors here. They have different space groups, and that's what we're going to talk about today, right? So this space group here, for example, is P2 1 upon C, and I hope that by the end of these lectures you will know what I mean when I say P2 1 upon C. Okay. So the question is, how do we describe crystals in terms of their symmetry?